What if I told you that everything we think we know about getting to Mars is wrong? Not the destination, not even the timeline, but the engine. Right now, as you're watching this, NASA is building something that has never successfully flown in deep space before. A nuclear reactor attached to a spacecraft pointed at Mars, and the people behind it aren't fringe scientists chasing a dream. They're the same agency that landed humans on the moon, that sent Voyager past the edge of the solar system, that put a helicopter on another planet and watched it fly. They're calling it SR-1, Space Reactor 1, and if this works, and NASA is betting that it won't just change how we reach Mars, it will fundamentally change how humanity moves through the solar system forever. To understand why SR-1 matters so much, you first have to understand the problem it's solving, and that problem is bigger than most people realize. Rockets are extraordinary machines. The engineering behind them represents some of the greatest achievements in human history, but when it comes to deep space travel, real deep space travel, not a trip to the moon and back, but months-long voyages to other planets, chemical rockets have a fatal flaw baked into their very design. The more fuel you carry, the heavier your spacecraft becomes, and the heavier your spacecraft becomes, the more fuel you need to move it. It's a vicious cycle, a trap built into the laws of physics themselves, and there is no clever engineering workaround. You can optimize, you can lightweight materials, you can design more efficient engines, but you cannot escape the fundamental math, and Mars makes that math brutal. Earth and Mars only align for launch windows roughly every 26 months. Miss your window, and you're grounded for over 2 years, waiting for the planets to come back around. Every mission is a sprint against orbital mechanics, a high-stakes race that gives you one shot every 2 years or you start over. Then consider the fuel requirements for a serious Mars mission. Even SpaceX's Starship, arguably the most powerful and ambitious launch vehicle ever constructed, a rocket that redefined what we thought was possible, would need multiple orbital refueling missions just to load up enough propellant for a single crewed trip to Mars. Not one extra launch, multiple. Think about what that means. You'd have to send up the same massive rocket several times just to fill up the tank before the actual journey even begins. The mission to get to Mars requires a whole series of missions just to prepare for the mission. It's expensive, it's complex, and every additional launch is another chance for something to go catastrophically wrong. This is the reality of trying to reach another planet using rockets designed around exploding chemical fuel. They work for getting off Earth. They work for reaching orbit. But as a long-term strategy for building a sustained human presence in deep space, they are fundamentally inadequate. NASA knows this. They've known it for decades. And in 2028, they're launching their answer. Space Reactor 1 is not a rocket in the traditional sense. It does not combust fuel. It does not explode. It does not produce the towering pillar of fire and smoke that we associate with space launches. Instead, it does something far quieter and far more powerful. At the heart of the spacecraft sits a compact nuclear fission reactor. This reactor splits uranium atoms, and the energy released by that splitting process is converted into electricity. That electricity is then fed into a propulsion system called ion thrusters. Ion thrusters work by taking a propellant, typically xenon gas, and stripping electrons from those atoms to create ions, which are electrically charged particles. Those ions are then accelerated by powerful electric fields and expelled out the back of the spacecraft at enormous velocities. The resulting thrust is extraordinarily gentle. It barely registers compared to the raw violence of a rocket engine igniting at a launch pad. But here is the critical difference. A chemical rocket burns for minutes. Ion thrusters burn for months, weeks and weeks and weeks of continuous, patient, relentless acceleration. And over those months, drifting through the silence of deep space, that gentle push adds up to something remarkable. Ion propulsion is roughly 10 times more fuel efficient than conventional chemical rockets. 10 times. That single number changes the entire calculus of deep space exploration. It means SR-1 can haul serious, heavy cargo across hundreds of millions of miles using a fraction of the propellant a traditional rocket would require. It means missions don't depend on those narrow, desperate launch windows in the same way. It means you can move things through space, large things, important things, the infrastructure of a future civilization. without needing to launch a small fleet of tankers just to make it happen. NASA has given this vision a name. They call it a railroad to Mars. The metaphor is worth sitting with for a moment because it's more than just poetic language. Before the transcontinental railroad was built across the American continent, moving goods from one coast to the other was dangerous, unpredictable, and ruinously expensive. It took months. Entire wagon trains were lost. The frontier was a place people reached through tremendous sacrifice, and sustaining any presence there was nearly impossible. Then the railroad came, and freight began to flow, and towns appeared along the tracks, and what was once the edge of the known world became something people could actually inhabit. That is exactly what NASA is envisioning for the inner solar system. Not a heroic one-time journey with astronauts planting flags and returning home, but a steady, reliable, continuous flow of supplies, equipment, and materials moving between Earth and Mars the way freight moves across a continent. Slow by rocket standards, yes, but efficient, dependable, scalable. SR-1's first mission is both humble and historic at the same time. After launching in 2028 and spending roughly 1 year completing its journey across the void between Earth and Mars, the spacecraft will deliver its payload to Martian orbit. Yeah, that payload consists of 3 helicopter drones, each one an advanced descendant of Ingenuity, the small experimental rotorcraft that in 2021 became the first powered aircraft to ever achieve flight on another world. Ingenuity was a proof of concept, a demonstration that flight in the thin Martian atmosphere was physically possible. These new drones are something different. They're not experiments, they're workers. Their mission is to survey the Martian surface from the air, covering territory that rovers could never reach, scouting for 2 things that matter enormously to every future crewed mission that might follow. The first is landing sites. Any future mission carrying human beings to Mars will need a place to set down safely, flat terrain, minimal rock hazards, proximity to resources. Aerial scouts can map that terrain in extraordinary detail, building the kind of geological picture that ground-based rovers take years to construct. The second is underground water ice, and this one carries the highest stakes of all. Water ice beneath the Martian surface is not simply a scientific curiosity. It is the raw material of survival on another world. Water means drinking water for astronauts, but more than that, it means oxygen, extracted through electrolysis. It means hydrogen, usable as rocket propellant. In a very real sense, finding accessible underground water ice on Mars is the difference between a settlement that can sustain itself and one that dies, waiting for resupply missions from Earth. These 3 drones, delivered by a nuclear-powered spacecraft on a year-long voyage, may be the most consequential scouts humanity has ever sent anywhere. But SR-1's first mission is only the opening chapter of a much longer story. NASA has been clear that this technology is designed to scale. The nuclear systems being demonstrated here are the foundation for future infrastructure, permanent bases on the moon that can generate their own power through reactor systems, long-duration crewed missions to Mars that don't have to carry every pound of propellant from Earth, and eventually human operations deeper into the solar system than we have ever reached. The reactor technology aboard SR-1 could one day power habitats, life support systems, communications arrays, the propulsion of ships carrying the first permanent Martian settlers. There is a version of the future, not guaranteed, not easy, but genuinely possible, where cargo ships move between Earth and Mars on something approaching a regular schedule, where the frontier is not a place humans visit once with enormous sacrifice and cost, but a place where people live and work and build, where the railroad metaphor stops being a metaphor entirely. SR-1 doesn't build that future on its own, but it may be the moment we decided it was worth building. SR-1 launches in 2028. 1 year later, if everything goes according to plan, 3 helicopter drones will begin flying over the Martian surface, mapping what lies below, searching for water, preparing the ground for whoever comes next. The railroad is being built. The question is whether we're ready to ride it. If you want to go deeper on how nuclear propulsion actually works, how ion thrusters compare to every other engine concept NASA has ever tested, or what a real Martian supply chain might actually look like in practice, subscribe, because that's exactly where we're going next. And drop your answer in the comments. Do you think SR-1 is the breakthrough that finally makes Mars sustainable? Or do we need boots on the ground first before we start building the freight line? I read everything you write down there, and this is genuinely a debate worth having.